So coding as a scientist, and this is me displayed on the slide. Yeah, I shaved this morning. So over the last few years, I've been interested in the impact of data on brain sciences. So brain sciences are interested, amongst other things, in our mental world. So things like cognition, emotion, or corresponding pathologies, autism, depression. This has been historically studied by verbal interactions, and this is basically psychology. Now, one thing has changed over the last few decades is that we now can image brain function. We can get quantitative recording of what's happening in the brain. And this is having a slow but deep impact on psychology and cognitive science. So I think it's a very interesting place to be at. And so we've been looking at what data processing can do to these fields and processing medical images. So to give you an example of a work that we've done, we've been interested in biomarkers of autism. So can you look at the brain of someone and conclude whether that person is likely to be or to have autistic syndrome or not? And so the way we work is basically we're going to compare the brain activity of many, many different subjects, and then we're going to use supervised machine learning, so basically computers, to learn how to discriminate autism from control. So in practice, to give you a bit of an idea of the engineering that goes behind this, the first thing that we're going to do is that we're going to extract brain networks. You don't know what this is, but what really matters for computation is that we're doing unsupervised feature learning and that we're fitting a fairly complex model, much more complex than a logistic regression, to 1 terabyte of data. So there's a bit of a computational challenge or algorithmic challenge. Then, once this is done, we're going to look at how we can parameterize the per subject's brain connectivity. And so this is when I get to pretend I'm a mathematician and to talk about things like information geometry and Lie algebra. If you're interested, let's talk about this offline. And then basically we do supervised learning on this. So we just take scikit-learn and apply it, because this is what supervised learning for us is. So this works, but there are strong limits to the impact that we're having on psychology or psychiatry. The first one is we cannot, by construction, outperform the clinician that defined autism or control, because these are the people who are giving us the definitions. So by construction, we can't do their job better than themselves. The thing is, the psychiatrists are not happy with their current definition. Brain disorders are defined by symptoms. It's an uncomfortable situation to define a pathology by symptoms. You'd like to define it by the attack to a tissue or by a mechanism. However, they're not ready to accept our black box algorithmic definition. We can tell them, I can predict whether somebody is autistic or control. They won't accept it. And maybe they're right. Maybe they shouldn't trust the black box algorithm, because it has a lot of moving parts. So the challenge that we face in the long run in this field is, can we get the practitioners to make their tools theirs? Because if we can do this, I think we'll have a deep impact on psychiatry. If we can't do this, the question is open. So as I said, science faces a quest for trust. And this has often been labeled as reproducible science. So Victoria Stoughton says that if it's not open and verifiable by others, it's not science or engineering. So people in this field, in computational science, have been talking a lot about computational reproducibility. The idea being that if you automate everything and control the environment, things should be reproducible, right? So let's automate everything. And as my boss once said, it's just a simple matter of programming. That boss sitting right here. Now, of course, it's a bit more challenging. And the reasons are that some operations work much better with a human in the loop. So labeling some things, some insights on data. So basically there are humans in the loop. Science has humans in the loop. The other and related challenge is that scientific research is an iterative process. So we have a tension between the desire for quick and easy interaction and the need for automation and replay. And I think everybody feels it in this community. So a long time ago, when we were working on 3D data visualization with Prabhu on Mayavi, I think the way we tackled it is that Mayavi's code base creates a strong link between its internal object model and the dialogues it exposes. So the code looks like the dialogues. The code doesn't look like the visualization, but like the dialogue. So we thought that was good, but that wasn't enough. So then Prabhu added a fantastic feature, which is the record mode. You would click on the record button, and then you would change things on the visualization, and the lines of code, the corresponding lines of code would pop up. So that's one way of going at it, so trying to basically record what people are doing. Another interesting thing that's happening is what's happening in the space around between code and interaction around all the Jupyter Notebook and all those ideas of mixing widgets and code. So I think there's going to be a lot of experimentation that's going to happen here, and I'm not exactly sure what's going to come out, but maybe this will help reconciling the need for interaction and the need for automation. So if we make every computational step reproducible, just good science will emerge, right? There's recently been a study that estimated the reproducibility of psychological science. So that's the title of the study. It was published in Science. And what they found is that 36% of the published effects reproduce. Only 36. And if you look at the problems, well, the number one problem is statistical challenges. There are many ways you can analyze the data. If you analyze the data in all the possible ways and you choose your best conclusion, your favorite conclusion, you will not control your error rate. That's basic statistics. It's easy to forget it when you think you're right. I always think I'm right. So I'm going to analyze the data, and at some point, I'll confirm the fact I'm right. And that couples in the fact that there are fairly weak incentives in academia. So you have to publish if you want to survive. And even the most honest people get fooled by this. I got fooled by this. So you end up, so the problem is the following. In the published literature, you have more false positives, more false finding that you think you have just because there's a selection bias. So it's an instance of winner's curse. So if you look at the problems here, very seldom is it a computational reproducibility problem. So we like to pick up the small numbers of cases where it's been a computational reproducibility problem. But the problem of science is not only computational. I guess that doesn't surprise you. So I think that reproducibility is a misnomer, or maybe just a too small concept. And for computational science, what matters is that operations are verifiable to build trust, and ideally reusable. That said, if we want to improve research, to improve science in general, the best way to do it is to use the right tools, whether they're the right software tools or the right conceptual tools, and to get people to use the right tools. It's a hard problem, by the way. The reason it's hard is that a research environment is so complex from a sociological standpoint and from a technical standpoint. The real roadblock that people face is really cognitive load, because researchers combine concepts from many different fields. If on top of this, they need to combine tools that are all different, shell scripts, MATLAB, Python, Stan, bugs. You probably don't know all these tools. I don't. So if you're sitting in this space trying to combine all these complex tools with all the corresponding complex theoretical concepts, well, the chances that you get it right are small, and the chances that you find the right tool for the right job are even smaller. So to summarize a bit, coding as a scientist, I think that the final code should be auditable in some way. This is hard, and ideally reusable, and this is also hard. There's quite clearly a tension between interactive computing and automating, and I think the main enemy is cognitive overload. Is that very different from the industry? I don't really think so. So the Silicon Valley has a bit of an attitude that, hey, if it doesn't work, if it works, you don't really need to know how it works. What matters is it works. I've solved the problem. That's partly true. It's not true for every field of application, but it's also harming the Silicon Valley because there is more and more resentment against the Silicon Valley. And I don't want to go too much into this, but maybe the last elections are related to this. One thing that the industry has and that academia does not have is when it has a problem, some industries can just shove more money to it. So they can hide some of those problems, but they're just shoving money to it. The problems are still there. So just to give you an idea of how I think about my work as a scientist using code, I have a very iterative way of working, and this is the list of steps that I apply one after the other. The first thing I do is I use a good editor and some form of linter in it. Way too few people do this. So the idea being, if you do a typo in a script that you're going to run, and that's going to run for 24 hours, and the typo is at the end when you're saving the results, you've just lost 24 hours of computation. It costs just about nothing to add a linter to an editor, so I think you should do it. Something that's also very cheap is coding conventions. You got to get in the habit, but I try no longer to name my variables single letters, so X and Y. And if you use Scikit-learn, you may have noticed that we use X and Y a lot. That's historical. Sorry. Version control. Version control is quite cheap. Worst case, you don't use it. Well, you should see the commit messages in my scientific repositories. I think 99 of them are called iter. But it's better than no version control. If you want to scale up, and if you want to build, good tool or good science at the scale of a lab, then reading each other's code is very important. Code review, that's well known. One step further, unit testing, because really experience shows that something that is not tested is either broken today or tomorrow. That's just true. And if you want to go one step further and share your results, then you can make a package with control dependencies and compilation and everything. So there's an increasing cost here. It's really important to avoid premature software engineering. As Katie mentioned in her talk yesterday, I don't think everything should be reproduced. I'd like to measure the amount of stupid ideas that I have compared to the amount of good ideas, but I don't think it's a good ratio, by the way. You don't want to reproduce my stupid ideas. So it's a trade-off between over-engineering and under-engineering. The first goal is to generate insights, or if you're into innovation, to move into new spaces. So experimentation is great for insights and proof of concepts. That develops new ideas. As those ideas become clear, you need to consolidate. The good news is Python is amazing for this. Python allows you to write horribly dirty code and also very clean and robust code. The important thing is that you need to progressively move. And I say progressively because it takes me years to know whether my ideas are good or bad. Really, it does. So basically what I do is I make things more and more solid. And as they become solid, I understand them better. And as I understand better, I know whether I want to throw them away or turn them into a package. So when everything goes right, and those ideas end up being solid, so that's like 1% of the things we try, then I think we need to share them, we need to make them reusable, and we need to turn them into a library.